Just mind if I try sharing my screen?
Yeah, go for it.
All right. Look okay, you can see my cursor.
Yep, all looks good. Cool. Well, let's try and stay on time. So we've only got 2 talks left for today, and the first is Evert Nasedkin. Is that correct? Yeah.
Perfect.
From the MPIA in Heidelberg. Yeah, and he's talking about characterizing the HR 8799 system with gravity. Okay.
All right. So thanks for having me here today, and thanks for all of the other talks that we've gone through today. To change it up a little bit, I'm going to be talking about directly imaged planets rather than a lot of the transiting stuff that we've done. In particular, the HR 8799 system. I will be talking about a retrieval study that we are working on, primarily using new gravity data from the VLTI down in Chile. All right. So just a bit of context, this is the HR 8799 system. It was originally discovered in 2008 by Christian Marois, and it's the only directly imaged system of exoplanets that we have with more than 2 planets. For a long time, it was the only one with multiple planets, but we have since found a few extras. It's a really interesting system, not only because of the number of planets, but their sizes, and the fact that we actually have somewhat decent mass measurements for them from dynamical and stability arguments. So we don't necessarily need to rely on spectroscopic masses. So we can use it to kind of test our models a bit better. And so the goal of this whole project is to present a systematic retrieval study of the atmospheres of all 4 of these planets to try to get an idea of the system as a whole. Just a bit of context on these directly imaged planets in general. They exist in a very different region of parameter space than your typical transiting planets. And all of them are going to be very young, very hot, and massive. This is the only way we can really image them now is because they retain some of their heat from formation. Their mass and temperatures are more similar to brown dwarfs than they are to what we would typically see as our terrestrial planets or Jupiter in our solar system. So we can use the brown dwarfs as another way of kind of validating our models and methods. And just as an interesting note to me is, if you think about it, most planets are not going to be transiting just because of geometry. So in the future, if we want to study all of these, we're going to have to work on direct imaging and direct imaging instrumentation to study a lot of these. So with planets in general, it's not necessarily clear how they form. In particular, a system like HR 8799, where you have 4 very massive planets. And so there's 2 kind of general pathways through gravitational instability or core accretion. And so the goal, ultimately, with a lot of these studies is to try to tie the current atmospheric properties back to their formation history. So in 2011, Karen Uber published this very famous plot kind of showing how the carbon to oxygen number ratio can act as a tracer of the location of formation. Of course, things are more complicated than this, but it's a first step in tying bulk atmospheric properties back to the formation history, which then might tell us something about the mechanism of formation. So how do we do that? How do we measure this? I'm going to go through this quite quickly here because we've talked a lot about retrievals today, but measuring the emission spectra of a directly imaged planet is very challenging due to the high contrast between the host star and the planet. So you need very complex instrumentation to do that. And in the end, your data quality is not exactly ideal. You still have rather large error bars, and so we just want to use a fairly simple model to try to understand some of the broad strokes of physics. And we're going to fit all of this data using an atmospheric retrieval, using the methods that have kind of been talked about already. So in particular, the model we're using is based off of Paul Mollier's paper in 2020, my supervisor, thank you, by the way, using petite rad trans, which we talked about earlier on in the workshop. And so you can see some of the parameters that were included there, but in particular, I want to highlight how our model includes a couple different species of clouds based on and uses the Ackerman and Marley 2001 model to kind of parameterize how these clouds are distributed throughout the atmosphere. And we also include scattering of the clouds, which is also rather challenging. We use a disequilibrium chemistry model, so it's an equilibrium model with disequilibrium carbon quenching, so that accounts for the carbon monoxide, methane, and water, where they can be quenched by vertical mixing. We also have a free chemistry model to compare this with. And we use a flexible 6-parameter pressure temperature profile, which is described in that paper. And recently we've added more updates to Petit Radtrans, including adaptive sized pressure grids, Hansen particle size distribution clouds coupled to the Ackerman-Marley model, improved collisionally induced absorption handling, and more. All of this is on the current release of Petit Radtrans if you want to play around with this yourself. So we have this lovely model, but we're still only as good as our data. So what do we have? So we have data from gravity. So this is an adaptive optics spectroscopic near-infrared interferometer at the VLTI down in Chile with up to 130-meter baseline. With gravity, we can observe all 4 of the HR 8799 planets, and it only takes a few minutes to get pretty good signal-to-noise on these. Our spectral resolution is about 500. There is a higher resolution mode, but we haven't taken data with that yet. And all of this is part of the larger exogravity project. Several of the other commonly studied directly imaged systems have been already have published papers on this. So that's BetaPIC-B, HR8799E, the PDS-70 system, and recently HD206893. So go ahead and check out all of those papers. So what do we have for data? We have all of these lovely K-band spectra from gravity. The first data was taken back in 2018 for HR8799E, and more has been taken since then. And actually tomorrow night, we're gonna do another observing run. So all of these, again, taken at a spectral resolution of 500 with about signal to noise of 5 per channel. So to put that in a bit of context, this is the K-band spectra for each of these planets. There is a constant offset between all of them. But what we really want to do is incorporate it with all of the existing archival data. So that's data from Sphere, GPI, and OSIRIS, as well as unpublished data from CARIS and AILS. So it's really critical with these retrieval studies to have a broad wavelength coverage in order to really get into all of the different parameters of the atmosphere, which are sensitive, to which different wavelengths are sensitive. So we've spent a lot of time figuring out how to best combine all of these data sets, including reprocessing several of the archival data sets. There was some known tension between the Sphere and the GPI data, so our goal is to try to reduce that and to make sure we really understand the data that's going into this retrieval. So we tried 3 different data processing algorithms, so these are angular differential imaging algorithms, to extract the spectra of all of the planets, depending on the data set. So that's CLIP, Pinpoint, both of which are PCA algorithms, and Andromeda. And I can't emphasize it enough that retrievals are only as good as our data. So not only do we need to know the spectra and the errors very well, from a paper in 2016 from Greco and Brandt, we really need to understand the covariances between the wavelengths of all of these spectra. If you don't do this, your posteriors are going to end up biased and artificially narrow, so you will very confidently exclude the true values in your retrieval. So we did that. We measured the covariance, and it's highly dependent on your choice of algorithm, as well as the instrument you're using and even the instrument mode. But you can measure this in the region around the planet and get some idea of what the correlated noise actually looks like. But your algorithm choice doesn't just affect the covariance, it affects the spectra itself. Depending on which algorithm we use, we found up to a factor of 2 to 3 difference in the overall flux, for example, in the GPI H-band spectra. And the different algorithms perform very differently depending on your instrument of choice or your separation. So depending on what your particular target looks like, you will want to try all of these and figure out which one works best for your data set. For us, we ended up going with the CLIP data because it performed well on all of our data sets and gave reasonable errors on all of the spectra. So yeah, we should study this more in the future. There was a paper from Cantaloupe et al. Showing how these algorithms affect the detection, but it needs to be really quantified further for the actual characterization. So we have all of our spectra now, so what are these planets like? So we fit the data using the nice Petit Trans retrieval, and we've done this for all of the planets, though there's still many more to go. So far, our results look relatively consistent with the literature values. All of the planets are cloudy, they're all in the expected temperature range of 1000 to 1200 Kelvin. And if we take that plot that I showed earlier for HR 8799E, we can update that with the values that we've retrieved and find that things are relatively consistent even after we've added some extra data sets. So that's a nice first check on what we're doing here. So going a little further into this, we want to really understand the chemistry of these planets. So far, the retrievals, we've only run a free chemistry retrieval on HR 8799B, so that's what I'm going to talk about for a minute here. So our fiducial model is the one from Mollier et al. 2020, which is the disequilibrium chemistry model. But we can compare this to a free chemistry retrieval where we retrieve the abundance of all of our species of interest. And if we do that and add this to the plot, we confidently detect water and carbon monoxide as expected, but there's also showing evidence for the presence of HCN and CH4. I wouldn't go so far as to say that these are confidently detected yet. We need to run further retrievals actually removing these species and to be very sure that they're there. But it's interesting to see that with the new data sets, we're starting to understand the chemistry better than what we were previously able to do. We also found a much higher carbon monoxide abundance using the free chemistry retrieval, and it's not entirely clear why, and this affects the carbon to oxygen ratio, as I'll get to in a minute here. And we think that this might partially be explained due to the differences in the retrieved effective temperature or the radius of these planets, which of course are correlated from the Stefan-Boltzmann law. Why these are retrieved differently between the models is still under investigation, and we still need to figure that out. Because a lot of our results are very dependent on our model selection, in particular the carbon to oxygen ratio. So whether we use the disequilibrium or the free chemistry retrieval, we end up with very different CO ratios, none of which are particularly consistent with literature values. So again, this is for HR 8799B. And using the disequilibrium model, we find a very substellar CO ratio, whereas with the free retrieval, we find a very superstellar ratio. And it's not clear why we are retrieving such different values here. But if we kind of put that caveat aside and just take the disequilibrium model at face value, we can update that Evert et al. Plot with the measured CO ratios for each of the planets. And what we see is there might be something of a trend there with the separation of the planets, though I will caution that the retrievals for HR 8799C and D are not actually done yet. This is just the current best fit after about 5 million models, and I don't know why they're not done yet. They're very computationally expensive. But interestingly, we find that the HR 8799B is rather substellar, which is not really expected given that Oberg model. And that one is actually a rather confident retrieval. We can also take a look at the metallicities. Again, cautions on the C and D planets, but we generally find that the metallicities are about 10 times the stellar value, which I would need to talk more to the formation modeling people to understand what we would really expect from the planets as compared to the disks. So with all of these retrievals, there's still many more retrievals that we need to run to become increasingly confident about the chemistry, but we also need more data. In particular, we need broader wavelength coverage, especially if we want to understand the clouds better. So future observations from the MIRI MRS could be a key part of this, extending our wavelength coverage all the way out to 28 micron. And this broad wavelength coverage will give us access to silicate features in the clouds at around 10 micron, From mock retrievals, it will increase our precision by an order of magnitude, and a lot of this is because we're able to measure individual molecular lines. So this will be very critical going forward, and hopefully we can get JWST time for this at some point in the future. So in summary, studying these directly imaged planets is very challenging, both from an instrumentation, a data processing, and modeling perspective. It's all very complicated, and it's important to do it in a systematic way to understand these planets. A single retrieval doesn't really tell us enough about these planets to say anything with confidence. We need to run many retrievals with many models to kind of find an overall picture of the planets and find robust results. And just to summarize, the results that we have for these planets so far were mostly consistent with literature, the temperatures again consistent, some possibly new chemistry detections, and a tentative trend in the carbon to oxygen ratio. And that is all. Thank you very much.
Great, thank you. It's really interesting. We had a question in the chat from Elia saying, are the observations with UTs or ATs?
I believe these ones are UT observations. You need to double check that.
Cool. I don't know what that means, but that's cool.
The 8-meter telescopes instead of the 2-meter telescopes.
Okay. Makes
There
sense.
are the ATs are the little Pac-Man telescopes you see on Paranet.
Oh,
Auxiliary telescopes.
Cool. Okay, we have another question in the chat from Dominique. There has been some back and forth on CH4 in HR 8799b. Could you please elaborate a bit more on your detection?
Sure. Problems we're using. So CH4, we've got, we have it here. We found that the disequilibrium and the free retrievals come up with fairly similar values, but it's at a really low abundance. And here I have the actual posteriors for this. If I just set the abundance to 0 in the free retrieval, the likelihood shows that the model with CH4 is very significantly favored. I'd want to rerun the free retrieval and see if there's another species without methane at all, and see if there's another species that can compensate for it. I had not yet compared the actual abundances to other published values, but that would need to be done. As far as I know, it's certainly expected to be a fairly low abundance, so I think that this makes sense. It's just a question of if we're really detecting it or not. And so far, it's looking like we are.
Cool. And we got a question from Matteo.
I have a question about your C2 ratio posteriors. When you also overplotted the literature values on top of that, those literature values didn't have any error bars. Is it because people haven't been running retrievals before, but just like compared to a small set of models? So there's no actual error on the C2 ratio? So
there's a few things. Some of these do have error bars, and I just neglected to plot it. Some of them do not actually have published error bars because they were before we really did good retrieval analyses on this, which is part of why we're doing this, is there's only been one real retrieval analysis of the planets.
Thanks.
Yeah.
Great. And then Bibiana?
Thanks, Evert. Really, really nice talk. It was really nice to see that you're still hunting down this time of 15 minutes, just hitting it exactly. That's crazy. He used to do that in his masters as well. Yeah, I have one question regarding the C over O ratio. I'm a bit confused there. You know, I'm working with much hotter planets, so this is all a bit help. Well, what is he talking about? But I was wondering, what does it indicate if these are different than the values that they have found before? Or you said that you also have this trend with separation, for example. Is this something formation indicating, or? Yeah.
So in the long term, that would be the goal, would be to tie a trend in the CO ratio with separation to say something about the formation history of the planets as a whole, or use it as an indicator for solid accretion rather than gas accretion, something about whether one of the planets formed beyond a snow line or something, something that in the formation process would fundamentally change the bulk composition of the planet. When we're comparing to the literature values, there I'd say it's more a function of what data is used and what models are used, both of which clearly have a major impact on what values you end up retrieving. And I'm finding that using the updated data has a very significant impact on the retrieved values. So it's going to be hard to say for sure what the true CO value is without really making sure we understand both the models and the data. And we need better for both.
Thanks.
Cool. Just very quickly, Emily's asked another question in the chat. She says, great talk. I'm just wondering if you or anyone else has compared the different processing algorithms, PyClip, Pinpoint, etc. The model fits look wildly different, which is unsurprising, but somewhat concerning. And I'm curious how large this effect is on other directly imaged planets / brown dwarfs.
I would say for directly imaged planets, it's a big difference. It makes a dramatic difference to your spectra. The paper that I'm thinking of was Faustine Canteloube et al. From earlier this year, and that it compared the ability of the different algorithms to detect planets. There's supposed, using kind of a community-based data challenge, there's supposed to be a follow-up to that to actually see how they characterize planets, but that hasn't been done yet. And the only times I've seen these algorithms compared is in the actual algorithm papers themselves, and they all take different approaches to showing how they compare to each other, and they all kind of come up with different results. So it's going to be very important to understand how these affect your data and trying to understand what your actual spectrum is. That's still a major challenge, yes.
Great, thank you. Okay, and obviously feel free to continue the discussion in the Slack channel. So now we can move on to the last talk of the day. And we have Xintin Yu. Please tell me if I'm pronouncing your name wrong.
Sort of.
Okay, how should I pronounce it?
It's all right. It's Xintin. Yeah, you're very close, which is good.
No, it's good to know. It's good.
Yeah.
Okay, do you want to share your screen?
I think I need to be a co-host because I'm not.
You should already be a co-host. Okay, now you're
now I am.
co-host.
Okay, here we go. 1 second. All right. Let me know if you guys are seeing my screen. Okay.
Yeah, that looks good.
All righty.
Okay.
So
Yeah. Sorry, I was just gonna introduce you.
Yeah.
This is Xintin Yu from the University of California, Santa Cruz, talking about how to identify exoplanet surfaces without directly seeing them.
Thank you for the introduction. So my name is Xintin Yu, and I'm currently a 51 PEXA B postdoc fellow at UC Santa Cruz. So this work, we would like to introduce this idea of if we can tell an exoplanet has a surface or not, but without directly detecting the surface. All right, so let's first start with the solar system, okay? So we know that the terrestrial planets in the solar system tend to have some sort of a surface, and with some surface pressure. And the most extreme cases here is Venus, which has a surface pressure of about 100 bar, but everything else have surface pressure much less than that, and with a very thin gaseous envelope. While for the giant planets like Uranus and Neptune, they basically, we would say they have no surfaces. Or if we have to find one, which is a gas or liquid or gas or solid transition, it must be over 1,000 bars. So it's a very deep surface, and they have very thick gaseous envelope. So what about planets just in between the sizes of the terrestrial planets and Neptune-sized planets? Just wondering, hey, where their surfaces are located, and are they closer to the so-called super Earths, which have very shallow surfaces, or are they closer to the so-called mini Neptunes, which have very deep surfaces and very thick gaseous envelopes? And this is really a big problem for the exoplanet community, as we see a lot of planets that have this kind of intermediate size, and they're very common, but we don't have any analog of them in the solar system. So we don't really know where their surfaces are located. So first question is, why do we care about, if these exoplanets have surfaces, and where their surfaces are located? The first, I would say, reason is the obvious one is, I would like to argue that at least I don't think there will be any complex form of life that can survive in a solely atmospheric world. So you might heard some buzzwords about phosphine Venus and some papers about that, but I think those papers would hardly argue that there will be anything more than simple microbial life on Venus, in Venus clouds, because it's just really hard to kind of maintain a biosphere without a solid or liquid surface. Second reason why we want to know surface, where the surface exists on exoplanets, is actually can tell us something about how a planet formed. So if you look at the current distribution occurrence rate of exoplanets, there are two series that exist the current occurrence rate. And this is a more popular one, the mass law theory, which basically says that for the smaller size exoplanets, it's just very highly irradiated. So most of its gaseous envelope are stripped away and leaving almost just a bare rocky core. And for the bigger size bump here, they are just less irradiated, so they get to keep their original thick hydrogen helium envelope. And the second theory, I think it's less popular for now, but we can't rule it out completely yet. It's the volatile rich world theory. So same thing for the small planets, but for the bigger planets, this theory added an ice layer into the interior model. And they claim that just by varying kind of naturally the ice to rock ratio, you can have this kind of distribution of planets peaked at around 2.4 Earth radii. So really, for the future, if we know the surface location of the bigger size planets, and for example, if we see no surfaces at all for these planets, then that will indicate maybe the mass law series holds true. While if they tend to have some sort of a surface of different levels, then that might mean maybe the second theory holds true. So it seems like really important, right? But it's just gonna be really hard for at least upcoming observations to do in the next decade. So transit technique, of course, the next hot thing in the next decade with the James Webb Telescope, Ariel, and still Hubble. It's going to be great at seeing the atmospheric composition of exoplanets. But however, this technique itself is just not very sensitive to planetary surfaces. And of course, clouds and hazes always make it worse. And we see a lot of clouds and hazes in already some of the planets. Direct imaging, as we heard about, just is actually nice. It's sensitive to the surface if the atmosphere is not too thick. But however, as you just heard about, it's very difficult to do, at least for the small size planets we're interested in, which is less than 3 Earth radii. And we're just looking to something like, maybe in 30 years, like LUVR, maybe it can have this capacity to really identify surfaces on small exoplanets. So how do we do this then? So we had this idea kind of from two solar system bodies, Jupiter and Titan, and two trace species in the atmosphere, ammonia and methane. So note that Jupiter is kind of the deep, no surface case, while Titan has a shallow surface of 1.5 bar. And both of these species, since they're in the outer solar system, they should be originated like original primordial species in the atmosphere. All right. Now we start, with some of these gases in the atmosphere, and we know that the sun is irradiating at them, so there will be some UV photons hitting this species, and that leads to photochemistry, which leads to the formation of photochemical products such as the nitrogen and the hydrocarbons for these two species. And then on the left, I'm showing you Jupiter because we know that there's no surface, diffusion, the photochemically formed nitrogen and hydrocarbons will just be transported to the deeper, hotter part of the atmosphere. And because it's a hydrogen-dominated atmosphere and it's hot there, the photochemically formed nitrogen and methane, hydrocarbons will just be converted back to ammonia and methane. And then these kind of recycled ammonia and methane just kind of goes up through diffusion again to replenish the photochemically lost ones. So in the end, we still have lots of ammonia and methane in Jupiter's atmosphere. Well, if you look at Titan on the right, since there's a shallow surface that blocks all the thermochemistry happening that could happen in the deep hot part of the atmosphere, the photochemical nitrogen has nowhere to go but to just fill the atmosphere. And in the end, now Titan's atmosphere is about 95 to 98% nitrogen, while the hydrocarbons has nowhere to go but to be deposited on the surface. And that's why we're seeing tons of organics on Titan's surface. And in the end, because this reaction goes on, there's nothing to replenish ammonia and methane. Eventually, we are expecting to see depleted amount of ammonia and methane. And indeed, we see no ammonia on Titan. We see some methane, but from the Cassini-Huygens data, we know that it's all coming from interior gassing, and it's definitely not primordial. So my idea was just, hey, looking at the dichotomy of these kind of planets and these two species, can we use maybe the abundance of these kind of photochemically weak species to tell us if an exoplanet has a surface or not? So to do this, we use a state-of-the-art photochemical model, and we run tests on a model planet K218b, both with and without surfaces. So on the left, I'm showing you a pressure temperature profile that we adopted for this planet. And for this work, we simply put kind of Teflon surfaces. So there's no surface atmospheric interaction at different pressure levels. And then we just cut the PT profile and run the photochemical model. All right, so let's look at the results. So here I'm showing you first ammonia. So this is a pressure mixing ratio plot, and the dashed black line is the just using thermochemical equilibrium to predict the amount of ammonia in this K218b's atmosphere. And the thick gray curve is adding in on top of thermochemical equilibrium, also transport, which if you went to the lecture yesterday in the middle, and then photochemistry on the top. And now we're adding a surface of 100 bar. You notice nothing has changed. And this is, we think, at the 100 bar surface level, it's still hot enough to fully recycle ammonia back to the atmosphere. And now if we're adding a 10 bar surface, you'll notice that, oh, okay, now ammonia abundance is decreased by a couple orders of magnitude. And we think this is because at this surface level, it's not hot enough to fully get all the ammonia back, but still it's hot enough for some of it to get back. So it's not completely gone yet. And if we put in a colder 1 bar surface, we're gonna see less ammonia. And same species that behave similarly to ammonia is HCM. And this is because HCM is a direct derivative of ammonia. So, you know, the more ammonia there will be, the more HCM, and vice versa. And then let's look at methane. So again, you know, we're putting a 100 bar surface first, nothing has changed, same as ammonia. And now we're putting a 10 bar surface. Okay, so still the same as the no surface case. So that indicates, okay, at this 10 bar surface level, it's still hot enough to fully recycle, get all the methane back into the atmosphere. And not until we put in a 1 bar surface, we start to see decreased amount of methane. And water behaves similarly as methane, also have decreased abundances only at 1 bar surface level. So I'm going to explain this in a little bit. And the hydrocarbons behave basically similarly as methane because they are just direct derivatives of methane. So more methane there will be, and there will be more hydrocarbons as well. But they are only sensitive to 1 bar surfaces and with decreased level compared to no surface case. And there are actually 2 species that have sensitive to one bar surface as well, but they actually have increased abundances. This is CO and CO2. So anyways, we can make these kind of plots for all the major and observable species in K218b's atmosphere. And then we're able to group them into 4 groups. And they're all sensitive to surfaces differently, some sort. And you might wonder, why is this happening? So let's go back to the Jupiter and Titan dichotomy again, okay? So this is not exactly what's happening in K218b's atmosphere because there's more oxygen. So this is kind of showing you a kind of simplified chemical network for what's happening in K218b's atmosphere. This may seem a lot, but the general idea stays. So the idea is still, all the photochemically fragile species. So consider here not only just ammonia and methane, but also water. For the no surface case, since there's not much to recycle them back to the atmosphere, they're all kind of turning into gradually the photochemically stable species. That's why we're seeing increased amount of CO, CO2, and nitrogen. And the second interesting I want to talk about is, you might have noticed, is the sweet point where ammonia and ammonia, nitrogen, and carbon species can be fully recycled. It seems different. So it's a little bit hotter for ammonia, or a little bit cooler for the carbon and water. So given these results, how can we use this for future observations to tell if exoplanet has a surface? So first, we did some sensitivity tests. We ran some different eddy diffusion coefficient profiles, some slightly different temperature profile, etc. And we were able to pull kind of 7 criteria that will stay for all these different sensitivity tests. So how this works is, once we have atmospheric characterization done, okay, we first look at the species that are sensitive to a deep surface, such as ammonia and HCM, and then we compare the observed abundances to the no surface predicted abundances. If it's similar, then we'll immediately say that there will be a surface, there will be basically no surface, or surface has to be at least as deep as 100 bar. And then we tend to, if it's less than the no surface predicted value, then we tend to species that are sensitive to shallower surfaces. And then we can look at these criteria to tell if this exoplanet has a shallow surface, less than 10 bar, or intermediate surfaces. So this is really nice because it looks like we can use just the observed atmospheric abundances of species to tell not only if an exoplanet has a surface, but also roughly where the surface is located. But so far, this flowchart just works for a hydrogen-dominated K218b-like exoplanet. And we're still exploring looking forward to model a range of different exoplanets, different chemical compositions, and slightly called cooler and hotter planets as well. But here are just my conclusions, and I'll just leave this slide for questions here. And that's it.
Great, thank you. That was really good. Does anyone have any questions, either in the chat or if you want to just raise your hand? We have a couple of minutes. Yeah, Nicholas?
Yeah, great talk, Xintin. I was just wondering, do you have a time scale for how this process might actually work on a planet that does have a surface?
It's very fast. So we use a more irradiated star. I think it's around 100 million years, if I remember correctly, but it's very, very fast. So we probably wouldn't even see it on a very young planet. But yeah, pretty fast.
We have a question in the chat from Dominique. It says, what kind of instruments / developments do you think we would need to be able to apply these methods? Or is it something we can do already?
This is a good question. So of course we need very precise atmospheric characterization. So we're relying on the big transit telescopes such as GWST or Ariel that can really do infrared and characterizing the atmospheres. And of course the hazes and clouds has to be cooperated across all the wavelengths. But yeah, I think in the next decade, we'll have some.
Great. Any other questions?
I think we're great on time. So
Yeah. Very impressive. Okay, if not, then yeah, this is the end of the first day. Well, yeah, first day of the workshops, I guess. Cool. Elia, I don't know if you have any closing statements.
Just one last thing. So the videos of the lectures from yesterday are almost up, and the material also on the program, so you can have a look at all the lectures and go through the IPython notebooks and the Google Colabs from yesterday too. Almost, there's just one left. All the talks were too interesting for me to work on other things. And for most of you have already sent me, thank you very much. Just those of you that haven't yet, at some point, once you get a chance, can you please email us your presentation so I can put it online. And remember, whatever you don't want to be put publicly online, just remove it before you send them to me. That's it. Thank you.
thanks all. See you tomorrow, I guess.
Great. Then yeah, I guess we'll
thanks.
reconvene tomorrow.
See you all tomorrow.
Thanks everyone.